Alright, this is just meant to be a quick tutorial on piecewise functions. Hopefully there's not a lot of background noise here and you guys can hear me. Obviously, the problem with piecewise functions is because they're made up of multiple pieces or multiple different types of equations that each of them is a little different from the other. So there are some things that you can remember as basic rules for all of them. Other parts of them are going to change depending on what types of equations you have. So these may not be the best examples for everything, but hopefully they'll help some. First one tried to start off with some simple equations, meaning if you look at the equations we've got here, we've got a 1, a 3, and a 5. These are all constant functions, meaning whatever values we plug in for x isn't going to change the output values that we're going to be getting for y. All we really have to do is make sure that we are following these inequalities right here, these guidelines for each of the two equations. Okay, as long as we do that and make sure we're careful with the closed dots, open dots, that sort of thing, we're probably going to be okay. So the way we go about with any piecewise function is just take each equation separately. So we're going to start with our first equation right here. That we've got f of x equals 1 whenever 0 is less than or equal to x is less than 2. Alright, that's the one we're going to look at right now. So in that case, I'm going to create a quick little xy table here. We don't super need it for this equation, but I just always like to create an xy table. So this one is for f of x equals 1. That's what this one is for. I would always recommend plugging in the x values that you have on your inequality, however many of those there are. In this case, we've got 2 of them, both 0 and 2. So I'm going to plug in both of those as x values. As always, x values, or xy tables, the great thing about them is that your x values are entirely up to you. You don't have to use 0 and 2. Now, eventually you're going to show those points because those are the boundary points for this graph, so we need to show them whether they are closed or open and such. But if I were you, I would always use those. But you don't have to. You can pick any x values you want, okay? But I'm going to use 0 and 2 because they were already given to me, so why not? Like I said, very straightforward with this one. There is no x value to plug into. It's just a 1. So since I can't plug in 0, the answer is 1. And since I can't plug in 2, the answer is also 1. Not very hard math overall there. It's just the concept. Now, the important thing is I need to look at my inequality symbols to see which of these is closed, which of them is open. Are they both closed? Are they both open? That sort of thing. Well, right here, this 0 is less than or equal to x. Since that's a less than or equal to, this is going to be a closed dot. Whereas it's just x is less than 2, not a less than or equal to. So because of that, that's going to be just an open dot. Those are both coordinate points. Right? That's the point of an xy table, is it gives you coordinate points. So let's go ahead and graph those. Here's a closed dot at 0, 1. Here's an open dot at 2, 1. Just connect the dots. There is 1/3 of my piecewise function graph, because I've got 3 equations. Okay, so we're done with that piece now. Now we're going to move on to the second equation, the 3 right here. I'm going to create another xy table for that, even though hopefully by now you understand why we don't really need one of those, but it's still useful. Run out of space there. Again, we can pick any x values you want. Now we are constrained by these rules right here. We are only wanting to pick numbers between 2 and 4. You can plug in other x values, but if you do, you're only going to be using those to get the shape. You're going to have to erase them later, which is kind of a waste of time, and if you're writing in pen, really not a good idea. So we only want to pick numbers between 2 and 4. My recommendation would be we actually use 2 and 4, because again, those are the boundary points. I know I'm going to need to figure out where this graph starts at 2, what that coordinate point is, and I know I'm going to want to know where that graph ends at on 4, what those y values are. So I might as well just use them as my 2 for the xy table. But you could plug in 3 if you wanted to, and that would still be fine. You could plug in 2.5, 3.5, any of that sort of stuff. Again, in this case, you're not really plugging in because there is no place to plug it in, so it's just 2, 3, and 4, 3. You're just kind of stuck with those. Now we already have a point at 2 because we had 2, 1 on my first xy table. That's okay though, because 2, 1 on the first xy table is an open dot, whereas if we look at these rules, this right here is a less than or equal to, meaning 2, 3 is going to be a closed dot. Remember, as long as you have one closed and one open, they can still be looking like they're on top of each other because open dots aren't really there, right? The point of the open dot is we're saying that graph's really going to like 1.99999 repeating. We can't really show that unless we zoomed in really tight, so we just put a closed dot on 2, or an open dot, on 2, 1. 4, 3. If we look at this inequality again, we actually also have a less than or equal to with the 4. So both of these dots are going to be closed for this portion of our graph. 2, 3 would be right there on the graph. 4, 3 would be right here on the graph. There's another piece of my graph, of my piecewise function graph. Now, we're ready to look at the very last piece, the 5. So we've got 5, f of x equals 5, when 4 is less than x is less than 6. Again, let's do an xy table. Now, once again, there's not a whole lot of use for it, but we still can label what our points are going to be. I'm going to use 4 and 6 for my x values because those are the x values I was given. You don't have to use those. You could plug in 5, you could do 5.5, 4.5, things like that. But if they gave you x values on the rules, you might as well plug those ones in. Well, in this case, you're just going to get 5 for each of them. However, it's just a less than on both of these. No equal tos, which means both of these are going to be open dots. So 4, 5 would be right here. And then 6, 5 would be right here. That would be your graph for this piecewise function. Just a side note, if you're looking for domain and range stuff, your domain, remember, is the x values. So if you're trying to do the domain, then we're looking at how far to the left and how far to the right does this graph go. Well, the leftmost point would be right here at 0. It's a closed dot, so it'd be a bracket. The rightmost point would be right here at 6. That's an open dot, so it's a parentheses. Your range then is the y values, so we're talking about what the lowest point is versus the highest point. How low and how high does the graph go? Well, the low and high points are also the left and right points, so we're still looking at this point right here, but since it's the range, we're going to use y values. Well, the y value is 1. It is a closed dot, so we've got a bracket. We have both a closed and an open dot here at 1. If you've got both, the closed dot is there, so you consider it a bracket. Closed dots supersede open dots. Looking up here again at our high point, we're not going to use the x value. Again, it's going to be the y value, so that would be 5. Both of those points, here and here, are open dots, so it would be a parentheses. All right. Now we've got one that's a little bit more involved. This one, again, is 3 pieces, just like we did before. But as you can see, these are legitimate functions, so we're really going to have to actually use our xy table to figure out what we're doing with this. Okay? So, let's get ourselves a graph set up here. There. All right. We're going to start with the first equation, the top equation, the negative x plus 1. So I'm going to create myself an xy table for negative x plus 1. Once again, you can pick what x values you want to plug in. Now, the important thing with this function, as we're getting into legitimate equations here, is we need to start thinking about the shapes of our graphs from our parent functions that we've talked about. If we look at negative x plus 1, that is a linear function because it's just x to the first, unlike the second equation that's x squared, so that's not going to be linear. But for negative x plus 1, that's just a linear function. So because of that, it's going to be a straight line. We know that all linear functions are just straight lines, which means I only need 2 points for this graph. You can put more on there, but once I have 2 coordinate points from my xy table, I can just connect the dots, and that will give me an accurate graph. That's not always the case. That only works for linear functions. Well, I know it does work for linear functions. So I'm going to use -10 and -3. Reason being, same thing that we did on the last problem. Those are the boundaries given to me by this inequality. Meaning this portion of my piecewise function is going to be graphed only between -10 and -3. Now you know the normal function of negative x plus 1 being a regular linear function, it would be going on forever both left and right, negative infinity to positive infinity, right? All linear functions do that. Because this is a piecewise, this inequality right here, the -10 is less than or equal to x is less than -3, that is constricting our graph and only allowing us to show a part of it. That's the whole point of piecewise functions, is you take graphs that you've already learned how to graph in the past, and you go ahead and you don't go ahead, but the function makes you constrict those graphs down to where it's only a portion of what you would usually show. So I'm going to use -10, -3 because that's the x values that it gave me. You don't have to use those, but that's where you're going to start and stop your graph. So if I plug in -10, well, that'd be a negative x, so it'd be the negative of -10 plus 1. Well, negative double negative would give you a positive 10, plus 1 would give you 11. -3 is somewhat the same idea. It'd be the negative of -3 plus 1. So, double negative would cancel it out to just 3 plus 1, which would give you 4. That does mean that we didn't try to make this graph big enough, so we're going to do this graph by 2's. Okay, I'm going to label that. We're going to make this 2, 4, 6, 8, 10, 12. Alright, which means then over here we're going -2, -4, right? You get the idea. 2, 4, -2, -4 type idea. Alright. So, -10, positive 11. We need to graph that point. So this would be -6, -8, -10, and then halfway between 10 and 12. Notice I am making this a closed dot because we've got this less than or equal to right there. Because it's less than or equal to, the -10 point's going to be closed. As opposed to the less than right here, with just being less than means it's an open dot. So -3, 4, halfway between -2 and -4 right here, open dot. Okay? Like I said, we know that negative x plus 1 is a linear function. So 2 points is enough. All we got to do is draw ourselves a straight line between them. And that is half, or not half, that's a third of our graph. Now we have to do the fun one. X squared minus 9. It's only between -3 and positive 3. Now, this is where it's important that you know your parent functions, because you need to think about what this graph is going to look like. This is x squared minus 9. That means this is a quadratic. Quadratics are supposed to make either that U shape or the upside down U shape, however you want to think of it. It's going to be curved. It's a parabola. Okay? So we can't just find 2 points here and then connect them in a straight line. That wouldn't be right for this graph. We're going to have to get more than 2 points. I do still want to start off by plugging in -3 and positive 3, because those are my boundary points. Okay? Now the nice thing is, they should both be the same answer because we're squaring. And you guys know that a negative number squared still gives you a positive answer. So -3 squared is 9 and positive 3 squared is 9. So with either one of these, we'll start with -3. -3 squared minus 9. Well, -3 squared is 9, and 9 minus 9 would give me 0. If I do it for 3, 3 squared is 9, minus 9, again would give me 0. Now notice both of these inequalities had a less than or equal to with them. So that means both of those points are going to be closed. Negative 3, 0, closed dot. Positive 3, 0, closed dot. I can't just connect those and have a flat line though. That's not what quadratics look like. I know this is supposed to be some sort of curved shape. So for me, or let's put it this way, if you've done transformations, think about the function x squared minus 9. The only shift there is going to be a shift down of 9 because the negative 9 is outside the parentheses. So my vertex should still be at 0, it'll just be down at negative 9. Either way, if I know that I'm looking for some sort of curve shape and I've got the two outer boundary points of negative 3 and positive 3, if I'm picking a random x value, I'm always probably going to pick 0 because if I haven't used 0 yet, I want to. And it's right smack dab in the middle, so it'll probably do a pretty good job of giving me an idea what this shape should be. If I plug in 0, 0 squared is 0, shocker. And then 0 minus 9 gives me a negative 9. So negative 2, negative 4, negative 6, negative 8, negative 9 would be right here. Notice that's a closed dot because it's not even part of the inequalities, it's in between, so it's definitely a closed dot. Well, now I can see this clearly is not a straight line. We've got more of a U shape. That's not perfect, but that's about what the graph should be looking like. Just to zoom in here for a minute. All right, from negative 3 to positive 3. From negative 3 right here to positive 3 right here. So that is our graph. But since it's an x squared minus 9, since it's quadratic, it's curved in such a fashion. Last piece we need to talk about is the 2x plus 1. Put a line here. We're going to make ourselves an xy table for that. Now the good news is we're back to a simple linear, right? 2x plus 1, not 2x squared, not 2x to the third, it's not square root of x or absolute value or any of that sort of stuff. It's just a 2x to the first power. So because of that, we are able to just go ahead and plug in 2 points and be able to graph off of that. So I'm going to use 3 and 5. Again, 3 and 5 are the numbers that we were given on our inequality here. If they're giving you 2x values, you might as well use them. I can already tell right off the bat, these are just less thans up here, meaning this is going to be an open dot for each of them. All that's left is to plug them in. That means I would have 2 times 3 plus 1. 2 times 3 is 6, plus 1 would be 7. And then the other one I have is going to be 2 times 5 plus 1. Well, 2 times 5 is 10, plus 1 is 11. So 3, 7, looking at the graph over here, 3, 7 would be right about here. And 5, 11, this is 6, 5 is halfway between 4 and 6. And then 11 would put it right about there. Because it's linear, we get to just connect it with a straight line. And we're done. That would be your linear or your piecewise graph for this piecewise function. We had 3 pieces. This one, pretty clear, there's 3 distinct parts to this graph. The idea is you take each piece individually, make an XY table like you've already done in the past for graphing before, and then just slowly add to the graph as you graph each piece on its own until you get all of them on there. The number one thing with this is you've got to pay attention to what type of function you have and think about what the shape should be, because since piecewise functions are only giving you a part of the graph, it may not look like the shape you're used to. Like, it was nice this x squared minus 9 turned into a U shape because we happen to have it in the center, but it could have been moved off to the left and you would have only seen a half of that. You would have only seen like a little one side going up. It doesn't look like a quadratic in that case, but it still could be. So you've got to think about what the shape's going to look like even when it's been constricted like this for a piecewise function.